Okay, so let's start. Yeah, maybe I can begin by recalling at least the main definition. So, okay. So a cut diagram on a surface, let's say sigma, is maybe it's better to close the window. It is quite windy today. So perhaps from time to time you will see the butterfly. So a cut diagram on a surface, sigma is a diagram, is an oriented diagram on this surface, possibly with boundary. Together with a map which goes from the set of the arcs of the diagram to the region which are the connected components of sigma, the surface, minus the diagram. And so this is the labeling map, because to each arc of the diagram it provides a region of the surface, and there are some rules that should be satisfied. First, if somewhere you have a crossing like this, and the overstrand is labeled by some region A, and here you have B and here you have C. If you have that somewhere, so a crossing on the diagram involving the region A, B, and C, it means that somewhere else on the diagram, you have a strand which is also labeled by A. On both sides of this strand, you have the region B and the region C. Okay, so this is the first rule. And the second rule is that if your arc have some boundary point within a region A, the incident arc should be labeled by the same region. And these two rules, I motivated them because those cut diagrams arise naturally when you look at broken surface diagram and you consider only the lower pre-images on the surface. It gives you the diagrams, and the label corresponds to the region where the highest pre-images belong. So you have this construction, and when you consider this construction, these two conditions are naturally satisfied. And actually, there is also some technical reason for why we need them. But it means that these two conditions correspond to local conditions which arise when looking at some broken surface diagram. But it is easy to construct honest cut diagram which does not come from a broken surface. And maybe today I can give a counter example.
I'm sorry, Benjamin, maybe you can very briefly recall how a cut diagram comes from an actual surface in S4, because I'm afraid that some participants may have forgotten that.
We call that true. Okay.
Uh-huh.
Okay. Sure. So maybe I can redraw the picture. So when you have a knotted surface in S4, you can, just like for knot theory, when to study knots in S3, you project it in a plane. You consider a generic projection in a plane. You can do the same for knotted surfaces. But if you do that, then you will project not on the plane, but on R3. And you will get what is called a broken surface diagram, which is an immersed surface in R3, but with some singularities. So maybe I will draw a picture of this, like this. Maybe you can put some dashed line here and here. So this corresponds to the immersion of a sphere in S3, in R3, but there is some self-intersection. And every time I have a line of double points, for each point you have two preimages, but which are coming from the embedded surface in S4. So among these two points, one is higher than the other, and I removed a little band around the line of. I cut a band around the lowest preimages. So this is just what we do for a classical knot diagram. When at a double point, there is a double point, which has two preimages, one corresponding to the highest preimages and one corresponding to the lowest preimages. We just remove a small interval around of the lowest preimage. And here we do the same. So on your sphere, I have removed some small annuli. So like this one, and I have another piece of surface inside. So I have just removed this annulus here. I have removed one annulus from here to here, a third one from here to here, and fourth one here. Okay? So this is the image of a sphere. And I can look at the preimages of the lowest at the locus of the lowest preimages. So here I have removed 4 bands. It means that I have 4 circles of lowest preimages. So it means that I have 4 lines on my sphere. So one corresponds to this removed band. So let's say like this. Another one corresponds to this preimages. And actually this one is here. one corresponds to this one, which is here, and the last one is here. Okay. And now I give name to the connected component of my surface minus the lines created by the pre-images. So here I have 5 regions that I call A, B, C, D, and E. If I look at the image of A here, it corresponds to this small disk here. B is what is between red and yellow. And between red and yellow, I have all this piece, which is B. C is between yellow and blue. Yellow and blue, it's here. And now here I have D, and E is what is inside the purple circle, so it's here. Okay? And now every arc, I labeled it by the region where belongs the other lines of pre-images. So for this red line, I see that it is inside this piece, which is labeled by D. So here, I put a label D. For the yellow line, the other pre-images is on this part, which is also D. The blue one has the other pre-images inside B. And the purple one, it's on this part, which is also B. Okay? And now I have a way to give an orientation for these lines, which actually depend on the local orientation of the surface near each pre-images, and also of the global orientation of R3. And just trust me, the orientation is like this. Okay? And every time you have a broken surface diagram, you can play this game and get a cut diagram. Here, you see that I have just lines. It is not really diagrams because there is no crossing, but it's because this broken diagram was quite simple. I had only lines of double points, but there are also 2 other situations that can occur. You can have triple points. When you have when you have 3 sheets that intersect, and here you have a triple point. And if you play the same game around this, you have first to give the over/under data near each line. So let's say that they have cut my picture is wrong here. So the vertical plane has been cut in 4 pieces. And let's say that this diagonal one is also cut. So yeah, my picture is not very clear. And I should remove these lines. Okay. So if you do this, so you will have 3 pieces of 3 pieces of your surface corresponding to the 3 sheets that are intersecting. One has no cut on it, so this is the horizontal plane because so I have on diagonal plane. I have 1 cut like this, so it will correspond to 1 line like this. On the vertical sheet, I have 2 lines of lowest pre-images. So I have 2 strands, but those 2 strands are intersecting, but one corresponds to a line which belongs to the diagonal plane, which is lowest than the horizontal plane. So it means that this cut, I recall it by saying it is undercrossing like this.
Which one is it the horizontal plane or the diagonal one?
It is the cut which, oh, right. Yeah, sorry, you're right, I made a mistake.
I think you just redrew the same thing.
I just redraw the same thing. So the lowest cost, yes, sorry. And this is how the crossing of the diagram appear. Okay. And the third kind of singularity that can arise when you are looking at some broken surface diagrams are branch points. Maybe I will draw it here. I have a picture like this. And if I cut a band around the lowest pre-images, I will get something like this. Okay. And at the level of cut diagrams, I will have a line corresponding to this cut, which just end here at the branch point. Okay. And if I just glue pieces like that, I get my cut diagram. Is that okay? So with this process, I can create a cut diagram for every broken surface. And because of the construction, because of the local construction, it will respect these 2 labeling rules. But there are some cut diagrams which does respect these 2 rules, which does not come from a broken surface diagram. May I erase on the right?
Yes.
So for instance, I can consider just a sphere. Yeah, I like to draw this to see that it is a sphere, but now I will just erase it because there is no line at all. There is no diagram on it. So this is a sphere with just one region, which is A. And I have another connected component, which is a torus, with just one circle, which is labeled by A, oriented as you want. And here you have just one region B. This is an honest cut diagram because I have no crossing. So the first condition is obviously satisfied, and I have no endpoint. So the second condition is also satisfied. And I claim that this cut diagram cannot arise from a broken surface diagram, essentially because here you have the sphere with no cut at all. So it means that in R3, I just have my whole sphere. And here's the torus. I see that somewhere it just goes through the sphere from under because I have a cut arc. But it means that somewhere I am outside the sphere. And when creating these circles, it goes inside the sphere. But there is no room for getting out of the sphere because I have no other cut arcs. So with that, I would have a torus which goes inside a sphere, but never goes out. So there is no broken surface diagram that can correspond to this one. So this shows that there exist some cut diagrams that are not coming from a broken surface diagram. Okay, so this is the first thing. So maybe I can write like this. So we have a map. So to the set of cut diagrams. And this map is not surjective. Okay? But at the level of broken surface diagram, there are some moves, the Roseman moves, which tell you, actually, if you have two broken surfaces which are describing the same knotted surfaces, then you know that they are related by a finite sequence of Roseman moves. So this is the four-dimensional counterpart of Heidemeister moves. So there is a list of 7 moves. Maybe I won't give the full description because it will be a lot of drawing, and on the blackboard it won't be very readable. But this move, I can translate it into the language of cut diagrams. And those I can draw. So Roseman moves on broken surface diagrams. They lead to moves on cut diagrams. Those moves, there are 7 of them. So the first one is some kind of saddle moves. If I have 2 arcs which has the same label and with corresponding orientation, then I can make a saddle move, keeping the label A here. So this is the first move. On the 6 other moves, they start with an empty piece of the surface, and it creates one of the following diagrams. So either you have just one interval like this, and because of the second rule, this strand is necessarily labeled by the region within it is. You can also create a circle with any label on it. And the other maybe are less important here, but you can create like this a circle with a strand which crosses it from below. You can also create a 8 like this. Two circles like this, or 3 circles like this. Every Roseman diagram, every Roseman moves just corresponds to a combination of these moves. So it means that if this map from broken surface diagram to cut diagrams, it leads to a map to the quotient by Roseman moves. On actually broken surface diagram up to Roseman move, it is the same as the set of knotted surfaces. But for it to be well defined, I have here to quotient by those cut moves.
So you probably mean knotted surfaces modulo ambient isotopy, right?
Sorry? Yeah, it's ambient isotopy, yeah.
Uh-huh.
Yeah. But just like the definition of cut diagram was locally corresponding to what happens for broken surface, but globally it might not come from a broken surface, those cut moves are just locally like Roseman moves, but globally they might not correspond to a Roseman move. For instance, so maybe I will now erase the moves, but just remember that one of the moves is just creating one small cycle somewhere. If now I look back at this counter example, it means that up to cut move, this one is the same as what I had before. But I can create a small circles labeled by B, because this is one of the admissible cut moves. And now, this picture actually is just corresponds to the broken surface where I have my sphere and my torus, which enter somewhere. Now this new diagram, it does correspond to this broken surface. So it means that now it is not as clear that this map is not surjective, because you have some cut diagrams that does not correspond to broken surface diagrams, but it might happen that applying some cut moves, it does correspond to one. So I really think that this map is not surjective, but it is not a clear. It is not as clear as before introducing the moves, and also it shows that some cut moves may not come from a Roseman move, because here I have made one move to go from here to here, but the reverse move is also a cut move, and here it comes from a broken surface diagram. But if I apply the move with just remove these circles, I get something which does not come from a broken surface. So obviously, this cut move does not correspond to a Roseman move. Okay? Yeah, so perhaps this was not that clear on my first talk, so I guess it was better to say it clearly, and also it gives the opportunity to remind everything.
Yes, thank you very much.
You're welcome. Perhaps there is one proposition. No, one definition first, because I introduced the group associated to a cut diagram, and this is an important thing, so maybe I should call it. So for any cut diagram C, we define G of C as the group generated by the arc of the diagram and with relation every time you have two regions A and B which are separated by a line which is labeled by C, like this, then you have the relation that B is equal to A conjugated by C. Okay, so you have the presentation of a group, so this defines a group, and this group is invariant under all the cut moves. This is just, it's very easy to check that. Okay, first thing. So proposition, if C comes from a noted surface S, then this group is isomorphic to the fundamental group of the complement of the surface. So this is an an important motivation for that. On one proposition, no, first a definition, again. Every time I have a path on my surface, I can associate an element of this group to any path on the surface, which is generic with regard to the diagram. So first, I want that the initial and ending points are not on the diagram, and the whole image is transverse to the diagram. To every such path, you can associate an element of the group. An element on the definition, I will just give an example. So you have your path on your diagram. This path will meet transversely several arcs of the diagram. So maybe here like this, then like this. Every time the arcs will have some label, say A, B, C, D. And you will just read the labels when you are running the path from the starting point to the end point. So first, I meet this strand which is labeled by A. So I begin by the generator A. Then I meet B. But about the orientation, actually, there is a sign which depends on the orientation. So if for this one it was A with a strand going upward, this one is going downward. So take the inverse of B. Then I meet C going downward, so it's inverse C. And then D. And since it is a product of generators of my group, it is an element of my group. And actually, there is a renormalization. There is a renormalization. So I will end at the end of gamma 1 is inside one region. Let's say it's inside E. So at the end, I add some power of E just for renormalization, but perhaps I don't want to, it is not important here. Okay, so every time I have a path, I can associate an element to my group and proposition. If gamma 1 and gamma 2 are two paths which are homotopic relative to their boundary. So they have a fixed endpoint, but you have an homotopy in the middle. Then the associated element in the group of your cut diagrams are the same. Okay? And this is like with this proposition that we could define the notion of longitudes, which you had a base point on your surface, and you are looking at just loops inside on your surface based at this base point. And if you keep the base point fixed, you are in this situation, and you can associate the longitude. And then I define minor invariant by looking at those longitudes and which were base point dependent. But to remove this independence and also to get some numerical invariance, we can make the, let's call it the Milnor business, which corresponds to looking at the Magnus expansion and consider the coefficient up to some indeterminacy. But perhaps I won't go in more details about that today, even though I will use the same kind of idea later, but just remember that I have some past with some fixed endpoints, and now to extract from it numerical invariant which does not depend on the base point, I make use of Milnor business. Okay?
So geometrically, when you have a path like that, so I assume that you push off the endpoints to up. You push them up and connect to the base point, which is somewhere in the top. Is that correct?
Yeah. Yeah.
Okay. Thank you.
Yeah. Yeah. Topologically, it means that you have your surface, you have a base point, and you first go straight to near your surface, but near to this point, not on the surface, but very close to it. You follow the path, but not actually. You push this path out of the surface until the end, and now you go back to the base point. Yeah, that's it. Okay. Okay, so this was matter from the last talk, and now I will start my my last part about self singularities on the case of link map. I lost some. Okay. So now from the beginning, I was considering embedded surface in S4. Perhaps I can also erase this. And now I will focus on link maps, which are somehow like knotted surfaces, but they are not anymore embeddings. You may have some singularities. So, second part is about singular link maps. And let's begin with some definitions. So a link map is a map F from a surface, which is made of a finite number of connected components. I call them sigma E. They are the connected component of sigma. Inside S4, such that, so for knotted surfaces, this map is an embedding, but now I am just, so it is a topological map, it's a continuous map, but I only ask that the image of each connected component are disjoint. So there might be some double points, even triple points, or even any kind of singularities, but only within a same connected component. But the image of distinct connected components, they are disjoint. Okay? So this means we allow singularities only within a same connected component. And also, since I am looking a map from a two-dimensional manifold inside a four-dimensional manifold, generically, I only have a finite number of transverse double points, and every time I have a double points because of these conditions. Both pre-images on the same connected component. Okay, so this is the definition of a link map. And now I have that, I can define link homotopy. Two knotted surfaces are link homotopic if they are connected by a path within link maps. This is, I can deform my knotted surfaces, sometimes with singularities, but only self-singularities, like for link maps. Okay? So this notion was introduced by Minor in his PhD. So now let's look at those link maps. I can play the same game as for the same broken surface diagram game for link maps. One can define for link maps. So it's exactly the same game. You just project on a transverse R3. But now you have some real double points. And And of course, in the previous pieces of a broken surface diagrams, there was no room for real double points. But so what happens near those points? Near the real double points, the picture is like this. So yeah, maybe the best thing I should just it is something like this. So here I have two pieces which are like this, and I plug them so that they merge this point. So this is this plus no, maybe I should. I have one piece like this and one piece like this, and I just get them together to get that. Okay, is that clear? And locally, generically, it's always project like this. So this is the only new piece of a broken surface that you do create when considering link maps. Okay? And then you have some more Roseman moves to handle these double points. And so that you can have a complete description of the theory of link maps as broken surface, self-singular broken surface diagrams up to an extended set of Roseman moves. But from that, you can also consider cut diagram associated to these pictures. And if you do that, what happened? So here, again, I have two sheets here.
So I don't really understand what you draw in this picture. So you have these two lines like parabolas. Are they do they represent self-intersections of the projected surface?
So here it is a piece of broken surface diagram. Okay. This point is a real double point. So it means that even before projection, it was a double point. And when you project, you have this double point with two lines of unreal double points. But on these two lines, you have swapped the over-under information.
So in the broken surface diagram, you must have a triple point.
Yes, not a triple point, actually, just a double point.
But it looks like it is the intersection of two parabolas in your picture.
It's intersection of two things. So one piece like this, which is This one is really this piece, okay, and the other this one is like this. I will draw it above. Okay, and now I just plug these two pieces so that this point becomes this point, and it is the real double point, which is also a double point in S4.
So in the broken surface diagram, you remove certain annuli, right?
Yeah.
And so where are these annuli in your picture?
This one and this one is for branch point. Yeah, perhaps. Yeah, perhaps I should draw the picture, but before removing the bands. So I have okay, so I have two planes which intersect in a line. In the middle, I have my my real double points, and here and here I have lines of double points, but since my two planes are intersecting, are really intersecting in S4, it means that they swapped their positions, their relative positions at this point. Because if they were not swapping them, I would have two planes which are tangent, but it would not be a transverse. I have erased it, but I won't have a transverse double point. For it to be transverse, they have to swap their relative position. So, for instance, on this line, here I'm saying that the blue one is above. So it means here is the red. So it means that on this line, this is the red one, which is below. So I remove a band from the red one, like this. But it will somehow merge at the double point. So this is why I have not removed a band, but a triangle. And on this part, the relative position have changed so that it is not anymore the red sheet which is below, but it is now the blue one. So I will have to remove a band from the blue one. And again, the band will be, actually it will be a triangle. So that I get this picture.
Thank you, it is clear now. So another possibility would be not to place this double point in the plane of the projection, so that it would look differently.
What do you mean?
So you have this information about over and under
Mm-hmm.
Ah, okay. Okay. Yes, maybe. Sorry, what I said didn't make any sense.
Okay. Well, I don't know. But yeah, perhaps there is. Actually, yeah, I'm not sure. I think this generically it will project like this. Okay, so now you will have this kind of pieces in your broken surface diagram. And if you want to look at the associated cut diagrams, it means that here you have removed the band. So you will have an arc which will end at the corresponding double points. And on the other sheet, you will have also a line which will end at a point. Okay? And now, at the level of labels, well, here these red lines will correspond to, will be labeled by A, where A is the name of this sheet. And the blue lines will be labeled by B, where B is here. You will have something like that. So you will have two endpoints at your diagram. But here, the second rule, the second labeling rule will not be satisfied because here the arc is labeled by B and not by A. But you have another endpoint and they are just somehow exchanging their labels. Okay? So now we will define cut diagrams allowing this kind of situation. So maybe I can give the definition. Singular. So every time I will say singular, it will mean self-singular. I will never consider a fully singular cut diagrams, even if I could. But here I am only interested into self-singularities only. So a singular cut diagram on the surface sigma is an oriented diagram B on the sigma and a map P, a labeling map from the arcs of B to the connected components of the surface minus the diagram. So actually, this just corresponds to regular cut diagrams. Okay. Such that the first labeling rule is satisfied, the same as before. When I have a crossing involving three regions A, B, and C, it means that somewhere I have an arc labeled by A, which has region B and C on both sides. So this rules is just the same. But for the endpoint, because here, this is the second rule that I may not satisfy. So the second rule become the endpoints of D are split into regular endpoints which just satisfy the usual labeling rule, which satisfied the second rule, and singular endpoints. On this singular, they are gathered in pairs. Because here I have clearly a relation between these 2 points, and this is part of the data. For the singular endpoints, they are paired. They come by pair. And for this pair, first I ask that they belong to the same connected component. This is a self-singularity condition. Second condition, I have this labeling. So the arc ending at P1 is labeled by the region where P2 is, and vice versa. So the arc of P1 is labeled by the region of P2. And the arc of P2 is labeled by the region of P1. And there is another thing I haven't said, but about the orientation, it is, if you look carefully at the picture, you will see that the 2 lines, they are simultaneously oriented to the point, or so either both orientation are inward regarding to the boundary, or they are both outward. But there is actually it is just because everything is the same except you have swapped the position of the two plane. So in your basis, you have exchanged 2 vectors. So for it to be still a positive one, you have to reverse the orientation. So if this one was going downward, this one has to be upward. So they are both directed to the boundary. Or it is just the contrary. But there is a correlation between the 2 orientations. So I have no place to write it, and I won't use it so much, but there is also this condition. Okay, so this is the definition of a singular cut diagrams. Is there any question about it? Is that okay, Sergey?
Yes.
Yep. Okay, so now I have this new object. Still, I can define the associated group. Oh, no, I forgot. Okay, so now I have singular cut diagrams, but I need to define some singular moves, and I just use the singular Roseman moves and translate them into the language of cut diagrams. Yeah, but perhaps it is not that useful. There is a way to. There is a set of nice moves. Do you want to see them, or you just okay with
as you like?
I'm not sure I will really need them, so perhaps I prefer to not give them to you, but they are on the papers, and actually they are really like the regular cut moves. Actually, just some local pattern, simple local pattern that you can make appear somewhere. And this pattern will involve some singular points. That's it. Well, if I need them at some point, I will give them, but just know that there is some singular cut moves, so that there is a well-defined map from link maps to singular cut moves up to singular cut diagrams up to singular cut moves. Okay. Okay, so now from singular cut diagrams, I can associate a group with the same routine, the same presentation, but it's not anymore invariant. It is still invariant under the regular cut moves, but not under the singular cut moves. But actually, this is normal because the fundamental group of the complement is not an invariant of link homotopy. So obviously, it cannot be true. But we know that the radius quotient of the fundamental group is invariant under link homotopy, and it remains true for cut diagrams. So one can define G of C with the same presentation for every singular cut diagrams. But it is not invariant under set cut moves. We define the radius quotient.
So
and the quotient is Rg of C, which is just G of C, so it is the group generated by the arcs of the diagrams, and with relation every time you have two regions which are separated by an arc of the diagrams, you have the relation of one region being the conjugate of the other by the label of the arc. So this is G of C. But now you quotient by all the relations of the form regions commute with all its conjugates. Okay.
I'm sorry. Do your singular cut moves involve cancellation of two real double points and cancellation of a double point with a branch point?
There is a move like this, yeah.
Both moves, yes? You also have some cancellation with branch points, or you don't?
Yeah. One of the move, if you have nothing, and now you have two strands with two regular endpoints and two paired singular endpoints.
Okay, thank you.
Yeah, this is one of the moves. Yeah. So in particular, you can create some paired singular points.
Mm-hmm. Thank you.
Okay, so I defined the radius quotient. So this is the biggest quotient, such that every generator commutes with all its conjugates. Okay. So this is a radius quotient and proposition. This group is invariant under all singular cut moves. Okay? And so this is, I would say, this is the right notion of group to associate to this kind of objects. Okay. In the regular case, when I had G of C, I was able to define meridian and longitude and peripheral systems. Here you can just do the same, except that every time you look at the image of in this quotient. Actually, it's not exactly true. For longitude, it is not just the image of a longitude within this group, but a coset. But except if you have questions, I don't want to go in more details here because I prefer to focus on something else. But yeah, basically, it's just like considering everything in this quotient. So one can define reduced peripheral system. And you can just play the same game to define minor invariant from this, except that to define minor invariant, we were using the Magnus expansion, which goes from a free group to the set of polynomial in non-commutative variable. Now, this map is not anymore well defined up to this quotient, but there is a version of Magnus expansion for, in the case of a reduced free group. The map M, it's R, to remember that there is something reduced here, which goes from the reduced quotient of a free group. So here the R is just, I'm looking at this quotient which allow every generator to commute with all its conjugates. And now you are still going to the series in n variables which are which does not commute, but you have to quotient by monomials with repeated variable. It means that every time you have a monomial where, let's say, x1 appears several times, then it is sent to 0. So you only have monomials with distinct elements. And here, so you can still send xi, small xi to big, to 1 plus xi. And for the inverse, it was sent to the inverse of this series. It was this. But now, all those monomials are sent to 0. So actually, it is just 1 minus xi. So this map is well defined and is actually injective. And with that, you can play Milnor's game, define Milnor invariant, which are, remember, the coefficients of the monomials that you get when you look at the image by this map of the longitude. And these invariants are indexed by the indices of the variables of the monomials you are looking at. But now you only have monomials with non-repeated variables. So it means that here you can only define Milnor invariants with non-repeated indices. It means that in the sequence of indices, there is no repetitions. Every index appear at most once. So like that, with that. One can redefine Milnor invariance for sequence with no repetition. And you can check that this Milnor invariant with no repetitions are invariant under all self-singular moves. But at the level of knotted surfaces, it corresponds to link homotopy. And this shows that non-repeated Milnor invariants are invariant under link homotopy. Okay, so this is a combinatorial way to prove this.
But for spherical link maps, you don't have any of these invariants, right?
Sorry?
For link maps of spheres, of 2 or 3 spheres, you don't have any of them.
Of course, because you have no longitudes. all longitudes are trivial. So this cannot be used to prove that you have actually no. Of course, we know that embedded spheres are all link homotopy trivial, but so yeah. So of course, all these invariants are trivial because everyone is trivial for the sphere case up to link homotopy. But even for concordance, because repeated minor invariants are also invariant under concordance, and this is an open question to have some noted spheres which are not concordant to the trivial one, but all these minor invariants are just zero because there is no longitude. So it only tells something when you have some higher genus surfaces. Yeah. Okay. You have any more questions about this? Because, yeah, actually I have several corollaries, but maybe I can now state one corollary of this proposition, which is purely topological. So I think it's a nice result of the cut diagram theory. Let K1 L1 and L2 be two three-component links. So there are links in S3. There are usual links, and there are three components. Actually, it's also true for two components and one component, but I don't know for more components, but for three components, I can claim something. So I have two three-component links. Then I can take the span of the link. So the span is just you consider your link in R3 inside S4, and you make a rotation around one plane of your R3. This will give you a noted tori in S4. So this is the span of L1. You can do the same for L2. So here you have two noted surfaces, which are both made of three tori embedded in S4. And I say that these two noted surfaces are link homotopic if and only if L1 is link homotopic to L2, right, or the mirror image of L2. Okay, and this is perhaps I won't give the proof, but basically there is three ideas in the proof. First, the fact that the minor invariant that we have defined for noted surfaces, in the case of a span link, of the span of a link, they are related, they are closely related to the minor invariant of the link. So actually, there was several minor invariants that I defined for knotted surfaces, but there was one new invariant. The new invariant of spun L1 is the absolute values of the minor invariant of L1. So there is a clear correlation between the two. This is the first ID. The second ID, what is the second ID? Oh, yeah. Yeah, of course. The second ID is the symmetries that you have for minor invariant for links. They are not true for knotted surfaces, but for minor invariants of links, there are several symmetries when you permute the indices, and you have to use them. And of course, the main ingredient is that for three-component links, minor invariants are complete invariants for link homotopy. So gathering these three IDs, you can prove this statement. And I like this one because, yeah, it's purely topological. It doesn't talk about cut diagrams, actually, even though I use them to define the invariant. Okay?
So do you mean cyclic symmetry or some other symmetries?
It's the symmetry when you permute the indices.
Cyclic or shuffle?
The fact that mu 1, 2, 3 of L is equal to
Okay. Okay, thank you.
Yeah, actually, because, yeah, just in one word. The connection you have between the minor invariant of L and the minor invariant of spun L just says that if those two knotted surfaces are link homotopic, they have the same non-repeated minor invariants. Then it means that up to sign L1 and L2 have the same minor invariant. But using the symmetries and one special ingredient, you can see that there is two cases. All the minor invariants are equal or they are opposite to all the minor invariants of L1 are equal to those of L2 or opposite to those of L2. And using the fact that the minor invariants are complete invariant for three-component links up to link homotopy, it says that L1 is link homotopic either to L2 or to the mirror image of L2. Basically, this is the proof. Is there any question? No? So, I don't know what time it is. Okay, so perhaps now I can move to my last part. So, in this part, I was just using link maps to consider link homotopy, to see that non-repeated minor invariants are invariant under link homotopy. But I was still speaking about knotted surfaces. And in my second part, I will really talk about link maps and how to define higher order curve invariants. So perhaps let's start here. Okay, so in this part, for simplicity, I will only consider link map on spheres. So my surface will be a disjoint union of spheres, but no torus or higher order surfaces. Actually, it is possible to deal with them, but then you have some more involved indeterminacy. So yeah, I think it's better here to just focus on the case of sphere. And I will define an invariant for linked maps. So let's consider a singular cut diagram C, which is made of a surface which is hence disjoint union of sphere. I have a diagram on it, I have a labeling map, and I have a set of paired singular endpoints of my diagram. So in particular, these singular cut diagrams may come from a link map. Not necessarily, but it can come from a link map. We fix R1, Rn a set of one meridian per component. Just like for peripheral system, I was choosing one meridian on each for each component. So here I do the same. So it means that actually I am just fixing one base point on each surface, on each connected component, on each S2. So which corresponds to fixing just a point on each connected component.
Does this point have to lie outside of the diagram?
Yeah, you're right. Yeah, totally. Okay. Then in that case, the reduced group, the associated reduced group, it is actually isomorphic to the reduced group of the free group over this R1, Rn. So this is actually a statement. But it is actually it is a consequence of the Chen-Milnor Chen-Milnor presentation that I gave last time. I said that not in the reduced case, but in the regular case, when I look at the nilpotent quotient, every time I consider a nilpotent quotient then I have a presentation with just one generator per component, and relations which were just commutation between a longitude and the meridians. And actually, this remains true if you look at the reduced quotients, but we can prove, actually this is a result by Abegger and Lin, that the reduced quotient, this reduced quotient is residually nilpotent. So it means that if you look at the nilpotent quotient, at some level, it will be isomorphic to the whole group. So you will have you will get the relations for the whole group. Okay, so this is this need a proof, but in the case of the reduced group, you always have a presentations which have one generator by components, and relations which are only commutation between longitude and meridians. But here we are on spheres, so there is no longitude, so there is no relations, so it is just the free groups. Okay. But the reduced quotient of it. Okay, so we have this, and this is why the sphere case is simpler. And now, remember that to define minor invariant, I was looking at longitude because they were corresponding to loops on my surface with a base point which was fixed. And I said that every time I have a path on my surface, it was corresponding to an element of my group up to only relatively to the boundary. So I needed to have some fixed endpoints, but if the loop is bad at some given points, then I was able to use it. Here I will do something like that, but I will just use my singular endpoints to be the fixed endpoint of my surface, of my path. So now for each pair of associated singular endpoints of my surface, so P1 and P2, there are two singular endpoints on my surface, which are paired. So it means that somewhere I have this, somewhere I have this. This region is named A, this region is named B. Here it's B, and here it's A. Okay? This is something like that. So for every such pair of points, choose two paths on your surface such that they both start at the base point I choose on the component where the 2 points belongs. Okay? Because they must belong to the same connected component because they are paired. So my no. I cannot take P1 and P2 because the Pi are already the fixed points. So let's call them Q1 and Q2. So my two paths, they are both starting at the base point. But alpha 1 is ending at Q1, and alpha 2 is ending at Q2. So it means that on my surface, somewhere I have Pi, and I have one path which starts here and ends at Q1. So this is alpha 1, and I have another path which connect Pi to Q2. Okay? And now I can just modify slightly my path so that it is not ending just at Q1, but just before, so that it belongs to the region A. And also for alpha 2, it just stopped before, so that the endpoint belongs not at the singular point, but somewhere inside B. So now I can consider the composition of alpha 1 and inverse alpha 2. So this is a path, this is alpha 1 reverse alpha 2. So it corresponds to this path, which goes from near Q1 to near Q2. And up to homotopy, this defines something which is well defined as an element of RG of C. Okay. Do you have any question about it? Actually, I don't know what is the resistive. So I can define this combinatorially, but at the level of topology, if my cut diagram was coming from a linked map, what does it mean? It means you have a base point outside your link map. First, no, I am not sure about the definitions. So no, this is not that. Okay, sorry. Actually, my first, I was true at the beginning. It's alpha 1, alpha 2 inverse. So this is, first I'm doing this path. This gives me a word. Okay, sorry. This is a product of the word associated to alpha 1 with the inverse of the word associated to alpha 2. So it means first I run this path and associate an element, and then I start here and come back to P1. Okay. And at the topological level, it means that I have my base point in S4. First, I go to P1, now I just follow the surface through this path to come near Q1, but in my link map, Q1 corresponds to a double point. So using this real double point, from there, I can switch to there, and now go back to P1, and now go back to my base point. So it gives you a loop, which is actually disjoint from the other component, but which is inside, except for the initial pass to the base point to P1 and the final go back. But you have a path which is in the complement of the other component, which mainly stay on sigma I, but switch the sheets. It just pass through the double point. Okay.
So if you don't want it to be disjoint from your component, then you can just go directly to this double point A1. You don't have to stop sometime before it.
You said that we don't need to go to pi I to pi.
No, QI. You can go directly to Q1 and not near Q1, but just into it.
Yeah. Since you are making a pass outside the other component, you can just stay on. Yes, you're right. Yeah. But okay. Yeah, you're right. Yeah, just I said that I stopped just before so that I can use the theorem I gave at the really beginning, where the endpoint was not on the diagram. That is right.
I see.
Okay, so this element has actually topological interpretations, and we can use them to define an invariant of the link map. And for that, I will define this element, it belongs to this group because it belongs to RG of C, but I said that it was the same as the reduced free group over R1, Rn. But now I will, since I am among this generator, I will just send R1 to 0. So it just means removing this generator so that it corresponds to the reduced fundamental group of the complement of the other component, not the one I am following to describe my path. Okay, this will help. So now SE of C as just defined as the sum for every paired singular points such that the two elements are on the component sigma E of a sign associated to the double point. I will tell it how it is defined right after, times the element I have just defined, minus 1. 1 is just the trivial element in my group. And this belongs not to to this, but to the module over this group, because I sum some element with some sign. Where epsilon of S is equal to 1 if the two arcs corresponding to the two endpoints are both oriented toward the boundary. And it is -1 if it is the contrary. Okay. So I can define this, and actually this is invariant under all cut moves. So this defines an invariant of linked maps.
But you have a choice of meridian, and also
exactly.
you have the ordering of the Q1 and Q2. If you rename Q1 into Q2 and
yes.
Q2 into Q1.
And yes, yes. Actually, the first thing is just what I was about to say, and now I realize I forgot to tell perhaps the most important ID. So, because here I use an ordering between Q1 and Q2. You're right. So, but the two endpoints are not ordered. So there is actually this defines an element, but only up to inversion, because if I reverse if I switch the 2 points, I will just get the inverse image of this element. Okay, so keep this for later. Remark. Is well defined only up to inverse. And the first natural ID is just to consider this element and its inverse, because we can make some choice. But actually, what we have done is to first we choose some ordering on the component. So we have this additional data. To decide between WS and WS inverse, we choose an order on the component. We choose an order on the component. Since the Magnus if this element is just trivial, then it is equal to its inverse, and there is no choice. Okay. Otherwise, since the Magnus, the reduced version of the Magnus expansion is injective, the image of WS by the Magnus expansion is not just one. It has some monomials, some non-trivial monomials. But these monomials are naturally ordered because we have chosen an order on the components. But the component, each component corresponds to one variable. So if you have an order of the variables, then you have the lexicographic, thank you, order on the monomial. Order by the lexicographical order, so that you can look at the first non-vanishing monomials. You can look at the first non-vanishing monomials. And among WS and inverse WS, the coefficient will just differ by the sign. We choose the one which has a positive coefficient. For yes. And the inverse, the coefficient of these monomials differ by a sign. We choose WS to be the one with the positive coefficient. And with that, we obtain not canonically, because it will depend on the order we have chosen on the components. But as soon as the components of my link maps are ordered, then I have a preferred orientation for the loop, which goes through the double point. Okay?
Mm-hmm.
Okay, so now with that, WS is well defined, not only up to inverse, so that I can consider I don't remember the notation I used. SI. Of S WS minus 1. Okay. Proposition, this is invariant. Under singular cut moves, but away from the base point Pi, Pn. So, like that, you obtain an invariant for link maps given with a basing. And actually, it's for ordered link maps. And by ordered, I mean you have an order of the component. And from now, we will always have an order on the component. So we'll keep this data. So we get an invariant, but only for link maps given with a basing, because the result will depend on the chosen meridians. Okay? So now we want to get rid of this dependence. Now we want to get rid of the basing dependency. And also to get computable invariance. And for both items, we can use Milnor techniques. Because with Milnor techniques, as soon as you have an element of your group, you can consider the Magnus expansion and look at the coefficients, but up to an indeterminacy which is defined using the lower order invariant. So maybe I will write this. So Milnor technique is for every, let's say, W inside a reduced free group, and we can remove one generator just to be in the same situation as before. And actually, you can do it even on the Z modules over this group, because it is just easy to expand the Magnus expansion by linearity. One can consider the coefficient of the Magnus extension of this, which maybe I will write it below to have more place. So you will call it kappa. It will depend of the indices, and it will depend, of course, of the element. So you can consider these coefficients. And take the tilt version of that as the class of path up to an indeterminacy which is defined as the GCD of that will be easier to write it with a big E. So you have a set of indices W kappa G W, where G is a subset, a strict subset of E. Okay. So this is what Milnor does to define Milnor invariance. Except that in the case of link, you have some meridian longitude commutation relations, so that in the indeterminacy you have more stuff. You have also circular permutations, but this is because of this relation. And now we are on the sphere case. There is no such relations, so we only need to consider this element. On doing that, you define invariants which are invariant by conjugation. And this is just what happens when you change your base point. You are just looking at some conjugation. Like that, you get invariance for W up to conjugation. And you get also numerical invariance. So we can do this for what we have done. So now we can define kappa of a set of indices E of E as kappa of tilde of this up to apply to the element. I call it SE of C. So we call SI of C. This is the sum of so this element. You can apply this technique to this element, and you get some invariant. So let's write the name of the cut diagrams. And this is invariant under a change of basis. Propositions. For every set E of distinct, not set sequence, of distinct indices, capacity of I is an invariant unbased singular cut diagram. So that you get invariant for link maps, for ordered link maps. Okay. So this is a generalization of the Kirk invariant, because the Kirk invariant just corresponds to the case where you have only two components. In that case, you only have monomials with one variable, because you have removed the variable corresponding to the component on which you are considering the singular points. So there is only one coefficient, and this coefficient just corresponds to the linking number, and this is exactly the definition of Kirk. So so we just generalized it by looking at higher order minor invariant, but for this element. I said that it was one generalization because actually there are other options. Almost 5. I think I will not have time to give examples, but in our paper we have several families of examples with explicit computations, so that we have some families of link maps which have all this invariant, which are vanishing until order n, and with order n invariant which is non-zero. But yeah, I won't have time because I still have to leave at 4 in a few minutes. At 5, sorry, and it's almost 5. But so perhaps I could just end with this idea. So here I have taken this whole element, which is actually a sum of elements, and I used the minor technique on this element. And it gives me a sequence of invariants. But actually, I can try to split this before making the minor technique.
So before you raise this, maybe I should say that this also generalizes Kashorky's beta tilde invariant. The abelian part of your invariant is precisely Kashorky's beta tilde invariant.
Sorry, can you repeat?
So Kashorky also had a certain invariance of link maps. So he had a beta invariant, which is just Kirk's invariant modulo 2. It's very weak. But also he had beta tilde invariant, and this beta tilde invariant is precisely the abelian part of your invariant. So if you consider it's, like Kirk's invariant, but with many variables. Okay.
Okay. Yeah, that's that sounds interesting. Look at this. But just let me finish. So another strategy is to split Si of C before using the minor technique. By this, I mean that SI of C, so this is a sum of, this is a linear combination of elements of my group, and I can just gather them as a linear combination. So this is a sum of elements of this with some coefficient. Okay, so it is just every element of this, by definition, I can just have an unique way to describe it like this. So now I can consider the set of pair rho C of G for all elements such that the coefficient is non-zero. So I just extract all the non-zero elements like this, and then apply minor technique to each element like this. And then I will get not only one element, but a family of elements corresponding to every such pair I have in this set. And so like that, you get so here, this is just an integer coefficient, and here some E of G. You will get a set with several pairs like this, and we define this as another invariant. What I wanted to stress is that perhaps this looks refined compared with this one, because somehow it is just we have split this into elements so that if I take the sum of everything here, I will get that. But this is not true. This is not true because of the indeterminacy in the minor technique, which depend on the element you are looking on. And it might happen that the indeterminacy here is better than for each of the elements here. And actually, we do have explicit examples which are distinguished by this invariant, but not by this one. And we have another example which are distinguished by this one and not by this one. So somehow, this is two different invariants which can detect distinct stuff.
But when you do the splitting, don't you have to consider conjugacy classes?
No. Actually, perhaps this is also why this one in some sense is weaker, because you need them to be. If you take the conjugation here, at the level of the splitting, you will make the conjugation on every pair independently, but the same conjugation.
But for a fixed, so you said that for each fixed element G, you do the Milnor technique, or did
Yeah.
So what happens if you replace the meridians? Is G will be conjugated to another element, and so at least this for different G which are conjugate, you get invariants which are not independent.
This is true that what you will get will be independent by conjugation, by independent conjugation on every term. So it will be more than what you want. But perhaps this might answer your questions. It might happen that in this set, actually this is not a set. Let's call it an unordered sequence, because you might have several times the same element. Because it's possible that you get the same kappa invariance for two distinct elements, for instance, because they are conjugated. And actually, in the Contour example, we have such that they are not distinguished here. It is what happened. Actually, you have two elements. One is a conjugate of the other, so that you have two pairs which have the same element here. Actually, you have one have sign 1 and the other -1, but here you have the same element. So you have, yes, two pairs. And if when you reverse the orientation of one component, it will just add a sign -1 to everyone. So here, it will just switch the two pairs, but you will get the same invariance. Whereas here, you will get just another all minus signs, which you will be able to detect. I'm not sure if I was clear enough, but
yeah, but it seems you have to go, right?
Yep, sir.
You have to stop soon.
Yeah. Yeah.
So would you like to continue?
So this summer I will not be possible because next week I am on vacation and my wife will strongly disagree. But now what I have left to say is very technical. It's just giving examples. So it is just drawing some. So I'm not sure it is worth having another talk. Or perhaps you can look at the example on the paper, and if you have, we can organize another discussion on the examples. But
okay.
Yeah, it's as you want, but okay. Now it's just giving example on computation of example to, in particular, to see that these two invariants are actually different.
So I would be interested to hear that, but I don't know if you're interested to continue and to spend time on preparation. I mean, in September.
Perhaps. Why not? Maybe you can ask me the question again in September.
Okay, sure, yes.
As I said to you, I was applying to get in the committee of the National Committee of CNRS, and I have been elected, and I am not sure of how much work I will get because of that.
I see.
So perhaps I prefer to wait for September to see how it goes.
Okay, well, thank you very much. It was very interesting. Thanks a lot.
Thank you for listening, and especially today. I think today I was less clear than last time.
So maybe I should mention that I see that you went much further than me. I just considered this reduced the grouping of the reduced free group modulo as a conjugation and modulo inversion, and that's it. And then I showed that it doesn't reduce to the abelian case, and that's all that I managed to do. So you went much further. It's very interesting. Thank you.
Yeah, thanks to you. Okay, but so you're right. I have to go. Okay. So thank you so much.